start with just any polishing or questions on Logisim. Make sure that we're all clear on what the components of those assignments were and what the function of some of the components in Logisim is. So let me start. Questions, preguntas, Fragen. Off the dome? Oh, dome. You're not really sure? Okay. Well, all right. So let's go through some of the components that you guys are definitely going to need to use for several of the things, right? So one would be the splitter, right? Which the fan out and the bit width are not always going to be the same, but most of the time are because you're splitting off individual bits. Okay. In my control unit for the CPU that I was building, I had 16 bits, but fanned it out only in 4 because I wanted to take each nibble one at a time because they each meant different things. But yeah, that's kind of up to you, right? So the splitter, of course, can also be a combiner, and you can just rotate it or whatever to get it oriented the way you want. Pins and are going to be your input and output pins. I would use the guys up here at the top because there really is only one object called pin, and the distinction is whether or not it's an input or an output. And of course, it can have whatever data width you want. And then the label, the radix, is just how it displays inside there, whether it's in binary, hex, or something else. Decimal, unsigned decimal, or octal, which is something we've actually never talked about octal. So what do you guys think octal is? Huh? Yeah, it's just base 8 instead of base 16. So there, instead of taking, and this is one reason I don't particularly like octal, everything would be a 0 through a 7 in octal, right? Because that's base 8. And then what that would mean is that each octal symbol would represent 3 bits worth of information. Well, 3 is kind of a silly number on a computer, I think. So, yeah, they are, but like we tend to organize data into powers of 2, not powers of 3 or multiples of 3. So, yeah, anyway. But some old machines, they use octal instead. So, okay, fine, whatever. It, you know, yeah. Now, what's really annoying there, right, is that no power of 2 is a multiple of 3, which means that, like, they're kind of incompatible in a sense. Yeah, Will. Yeah, I don't really understand some of the circuit level stuff here, 3-state, whether or not you can have like, um, well, okay, so I'll give you an example of this. So some like solid state drives, for example, right? When they say multi-level cell, what do they mean? Okay, so who's bought an SSD recently? Yeah. Okay, so what's SLC, MLC, TLC, and QLC? No idea? Well, okay, fine. Let's go shopping. Huh? Okay, so let's go shopping. I'm switching over to Safari. Okay, so let's go shopping. All right, so we want to buy an SSD. All right, here we go. This one's going to be ballin' fast. Okay. All right, and let's look at the 1 terabyte one. Okay. They're on back order. Okay, big shock. But these things are going to be, this particular one is going to be freaking fast because it's PCIe Gen 4, right? Which, okay. So the memory components, uh, Samsung markets this as VNAND, and I'm not entirely sure exactly how they build their cells. But let's go back and look at a couple of other ones, right? So let's just say internal SSDs, all right, and then we want something that's sold by Newegg, so we don't get and shipped by Newegg, so we don't get stuff from that's like from some scrubs. Okay, so if we look at like for example this Intel one right there, right? Uh, you see it says QLC right here. Okay, so what that means is that each cell in the memory can actually store data at 4 different levels, and it's 4 different voltage levels, right? 0 would be off, sort of voltage level 1, 2, and 3 would correspond, therefore, to, so what can you do with that? With the single physical voltage, if there's 4 options, then how much data is encoded with that? Huh? If it's 4 options, 0, 1, 2, 3 are the voltage levels for that single cell, then that single cell can encode, well, let's make sure we got this right. It encodes 4 bits worth of information, right? Let's make sure that that's right. No, 4 bits worth of information would encode 16 patterns. 2 bits worth of information. Oh, how is it that they do this? Well, yeah, that's true, right? If only we had a website called Google. Here we go. Let's see, where does it do it? I wish they had a picture. That's what I was looking for. Um, okay, so VNAND is a triple level cell. Okay. Um, so let's see. There's, I know I've seen pictures of this. Okay, here we go. Micron for the win here. No, that's not what I wanted. Okay, their picture here. Um, okay, so sorry, I think I said it backwards earlier. So a single level cell, right? You can have 2 voltages, 0 or low or high, and low indicates a 0, high indicates a 1. Okay, multi-level cell, you can have 4 voltages, and that allows you to encode 2 bits worth of stuff. Does that make sense? Right. So 0 would be 0, 0. Level 1 would be 0, 1. Level 2 would be 1, 0, and level 3 would be 1, 1. Okay. So 4 voltages, 2 bits. Right. Okay. So if you want to encode 3 bits, how many voltage levels do you need? 8 of them. Right. If you want to encode 4 bits, you need, in a single cell, you'd need 16 voltage levels. Right. Which is a lot, and also kind of a lot to keep up with, because it's not as if you go from 0 volts to 100 volts on this stuff, right? The voltages on most computers are going to be, pretty much every component is going to be operating at like 5 volts or under, right? Most of your processors, certain parts of it's operating at like anywhere from 1 to 3 volts, depends, right? and um, right, because what happens if you double the voltage? By the way, what's power? Remember, it's too early to remember. Well, it's voltage squared divided by resistance, right? So if you double the voltage, you quadruple the power consumption. Well, that's not a good thing in a computer because if you quadruple the power consumption, then what? You quadruple the heat output, right? And that's not a good thing, right? Okay, so yeah, so I don't think you could model this in Logisim, but this tri-state stuff is basically sort of gets at the idea that you can have sort of multiple voltage levels. Um, and how the QLC they're able to make this work is kind of magic, frankly. But yeah, anyway. Um, so yeah, I mean the downside to it is it's a little slower in terms of um, uh, the it's a little slower in terms of reading and writing to that data or to that cell. But what's the benefit? Huh? What's the benefit to a construction like this? Yeah, you don't you can encode more stuff with a given number of cells, right? So your data density goes up, right? And that means you can either store more stuff for equal amount of money or more cheaply store a smaller amount of stuff, right? Just either way. Okay. Um, yeah. All right. So let's go back to Logisim. Um, okay. So we got the splitter, um, the clock. Um, you're not necessarily going to include an actual clock in your circuits, but if we wanted to then like use them, we would need to have a clock because when does all the magic happen in terms of uh, registers or D flip flops or things like that? When does the magic happen? On the rising edge, which means when it goes from low, the clock goes from 0 to 1. That edge is when the magic happens. Now, it is certainly possible to do things where it would also work on the falling edge. Okay. Um, and you could do that by, for example, not gating your clock because then the clock's upside down. And what the falling edge is on the not version is really the rising edge on the not version is the falling edge of the other one, right? So it's possible to do that. Um, and that, you can speed things up. Um, if you do that. But okay, so you won't necessarily have a clock itself, but several of the circuits need to have a place that the clock would get plugged into if we were to put this together into a larger circuit. Okay. Um, then I don't think we can use any of the others. I mean, they do have transistors here where we could go down to the transistor level to build some stuff up, but and if we had like another month or so, we do that. But alas, um, okay, and then let's see, gates, right? You've got all your logic gates, the and or not, and so on. I used a controlled buffer quite a bit because it basically allows you to connect or disconnect a thing. And so, for example, if you've got like, you would want to use this for um, if we were building, say our CPU, and we had the memory unit outputting data and the ALU outputting data onto the data bus, well, that's a problem, right? If two different things are trying to output data onto the same set of wires. So what would we want to do? We'd want to disconnect one of them or the other, or maybe even both, depending on what data should be actually on the bus. Does that make sense? Okay. Um, and then let's see, program a logical array. We never used one of those. Nor did we use the odd or the even parity thing. All right, plexers. So let me plop down a multiplexer, a decoder, and a demultiplexer. Right. So what's the difference between a multiplexer and a demultiplexer? Hmm? Yeah, the direction. Now, in a sense, there's not a whole lot different with them, right? So, because it's not as if wires are unidirectional type things in a sense. But what's the whole point of a multiplexer? You connect multiple things to a single output line. Okay, whereas a demultiplexer, you're using if you want to connect a single input line to multiple things. Okay, and then the dot that's down there at the bottom, what's that the connection point for? Well, okay, in the particular here, the default right are 2 to 1 or 1 to 2 splitters. So if that's the case, if it's 2 to 1 or 1 to 2, I've got either two inputs or two outputs, right? How many bits do I need to describe two things? Just one bit, right? So the thing at the bottom right is my selection bit, okay, which tells the circuitry, right, which one I actually want connected to the output. Okay, now this is just 2 to 1, but what kind of multiplexers or demultiplexers are you going to need in several of the circuits? Well, like let's say, for example, the register part of the circuit. There, what would we need? How many registers do we got? 16, okay, which means how many selection bits would we require? 4, okay? And that makes sense because, like in the Brookshire architecture, what if there are our opcodes, right? How many bits does it take to encode a single hex character? It took 4 bits. Okay, so there we would crank this up and we'd say, okay, data bits 1 or 8, depending, and select bits 4 would give me a 16 to 1 or 1 to 16 on the demultiplexer side, right? Same thing. Okay, does that make sense? And then what's helpful here is it tells you what the order is because it puts a little 0 where the 0th bit goes, and then they go in order from there, right? Which is kind of handy. But you can also select location, so that's where the selector goes. You can change that to be at the top if you want, if that makes it more um, convenient. And then you can also include a disable output, right? Which basically puts a buffer, connects a buffer to it. You can make that a separate physical entity, or you can kind of build it in like that if you want. That's sort of just, convenience if you want. And then you can make it narrower or wider, right? Just to fit things in. So, um, yeah, okay. Then what's the difference between a decoder and a multiplexer or demultiplexer? Well, the decoder has an enable built in, basically, and the select bits, right? So the decoder, so let me put this guy here, and we want select bit. Okay, so let's compare these two guys. What's the difference? They both have 16 outputs. Okay, but what kind of outputs are they? For a decoder, what can the outputs be? Only single bits. Okay. Also, what's missing from the decoder? There's no input. Okay. So all the decoder does is it outputs a 1 to precisely one of the outputs pins, depending on what the input selection bit pattern is. Okay, so if I were to, let me put an input here, and let me say this is a 4-bit input, right? So let me connect that to this dude, okay? And if I change that bit pattern, what happens to the decoding? Can you guys see the little green dot, right? So the decoder, if it's enabled, which it has an enable built in, or disable, I guess maybe better put. So what does a decoder output? It outputs a single bit, that's a 1, and which bit gets enabled depends on the input pattern, okay? So the decoder is going to output precisely 1 bit as a 1. The question is just which bit. Yes? Okay. What about the demultiplexer? Demultiplexer, it's about which output is connected to the input. Okay. The input could be a 0 for all we know, right? So the decoder is basically like if I put a constant of 1 right here, right? It's just a matter of which one am I selecting. Okay, does that make sense? All right, so decoder, I don't think you guys are going to use a decoder in any of the circuits that I asked you guys to build, but you will be using a demultiplexer in a couple of places. Okay, demultiplexers can have different bit widths, right? I mean, really what you're doing is you just have a demultiplexer for each bit, right? So it's this big unholy demultiplexing circuit, but does that kind of make sense? Yeah, no, okay. Okay, so let's delete that. Right. Okay, so we talked the plexers. Um, there is this special one, a bit selector that can you can pluck out a bit. That's kind of like using a splitter, picking the bits you want and then recombining. It's a little more convenient to have it as a single unit. So, okay, I don't think we need any of that for our stuff. For arithmetic, so you guys aren't going to use these, but it does have a built-in adder, right? And so um, what are the inputs, the outputs here? Right? So if I had a full adder, what would I need? I need 2 inputs, right? Because I'm adding 2 bits together and therefore 1 output. Okay, but what other inputs do I have? Well, no clock. The clock would determine whether or not I read or write that information, but just computing it is clockless. Yeah, so possibly I have a carry from the previous bit position. That's up at the top. And I have a carry that I need to output to the next bit position. That's at the bottom. Okay. So basically, you guys are going to build that thing as a primitive from and OR gates and stuff, right? Okay, but it's built in. Okay, so why am I making you build it if it's built in? To punish you? Huh? Would you say it's punishment? No, it's character building, right? Yeah, exactly. You guys learn how the thing works if you build it. Yes, educational. Um, let's see how to put this. Yeah, character building. Character building. Okay. Right. So you've got that, but what's nice is that it does also have some of the other things. So shifters. Um, the a shifter, you'd have the bits to be shifted, and then how far to shift them. and then the shift type, right? So what kind of shift operator do we have on the Brookshire machine? What kind of shifting do we do? Right. It's to the right, and what kind of shifting is it? Not which direction. It's, what does this mean? It's rotating, right? So if I shift to the right, what happens to the bit that's on the far right? In Brookshire, it comes all the way back around to the front. So that's a rotation, not a shift, right? Okay, so there are 5 different options for shifting that we could theoretically have, right? Brookshire is the bottom one, rotate right. How did we do rotate left on Brookshire? So if I wanted to rotate left by 3 positions, that's the same as rotating right by 5. Yeah, we used our noodle, okay. Brookshire did not have logical or arithmetic shifting, but we could get them. So what's the difference here? Logical left and logical right, okay. What happens, say, with logical right to the bit that's on the far right? He disappears. Okay. Well, then the bit that's on the far left, who gets shifted into that position? Right? Because it's not like there's a 9th bit or something. A 0 gets, if it's a logical shift. Okay. So if you take 8 bits and you shift them one position, so the 8th bit falls off, who shifts into the 8th position? A constant of 0 in the case of a logical shift. Okay, does that make sense? Okay, so then what's an arithmetic shift? That's a good question why they only did that, because let's see, why would they have done that? Because I think a left, because a logical left and an arithmetic left are the same. You just put a 0 at the far right end. So there's no need for it. Right? Yeah, okay, because so Porter's question is, why is there no arithmetic left? Well, the reason is, first off, how does an arithmetic right work? Let's talk that. Okay, so arithmetic right works like a logical right. Okay, what's different though is what happens to what do we put in the new 8th bit position? Should we put a 0 or should we put a 1? Huh? Exactly. You put whatever it was before. Okay. So if it was a 1 before, you put in a 1. If it was a 0 before, you put in a 0. Okay. This is why it's called arithmetic, because what's the 0 or 1 in that final bit position tell you? Whether or not it's positive or negative. Okay. And so if you shift to the right, that's tantamount to dividing by 2, right? Okay. In the same way that if you shift all your digits in base 10, what's that the same as? Or shift them to the right. It's the same as dividing by 10. We? Right. Did I ever tell you guys the story about um, when I worked at Kohl's?
Oh, the lady that told you it's 90%?
Yeah, the lady that came up to me with a bunch of stuff that was supposedly 90% off, and she wanted to know how much it all was, which, to be fair, like, how many of you guys have shopped at Kohl's? Okay, how many of your moms have shopped at Kohl's? Okay, that's what I thought, right? Yeah, you do. Okay, but because of all the deal nonsense that they do, it is somewhat tricky to know when they say it's 90% off. Well, 90% off of what? Right? That's not always clear when and especially when they're like, take an additional 25% off this, 37% off the whatever, right? Right. It does get a little bit complicated. Okay, but fundamentally, this is the simplest thing. Any of the discounts, what are they all relative to? The original price. Now, where do you find the original price? On the tag? No, on the tag or the barcode. right? Where it says orig and then a number, or MSRP and then a number, right? That's what everything's based off of, okay? So if it's, so she brought me a stack of things that all had barcode stickers on them, right? And, let's say that this pot is $30. Well, I just shifted the decimal point, or equivalently shifted all the digits to the right, and then 30 became 3. It's $3, ma'am. Great, thank you. Right? So then she was amazed when I was able to, she brought back like a cartload of stuff, and I'm like, 253, well, just going burning through it. She's like, how are you doing that so fast? I'm like, well, ma'am, 90% off means 10% of, and I'm just shifting the digits. Oh, you must be really good at math. And I said, well, I am a math major, so yes. Oh, yeah, right. Good is a relative term there, right? Okay, so right, so that's why in an arithmetic sense we would want to do shifting, okay? But in a binary world, shifting to the right by one position does what? Divides it by 2. Okay. Well, okay, divides it by 2 and does what with if there's a remainder? It discards it. There is no remainder, right? So 5 divided by 2 is 2 remainder 1, right? But if I thought about that as doing a shift, then it would be 2. That's it. There's no remainder. Okay. Which, by the way, what can the remainder be in binary? 0 or 1, right? And that makes sense because it's a single bit that fell off the wagon, and that bit is either a 0 or a 1. Okay. All right. So let me actually make a let's look at the difference between the shifts. So let me make an input, okay, and I'm going to put this in, I'm going to make this say, let's do 8 bits, right? Okay, and then let's look at the difference between the different shifters. So, so let me do a logical right. I'll also do an arithmetic right, and then I'll also do a rotate right. Okay, is that okay? All right, then I'm going to connect my input to all of these guys, right? So it's, um, they're all going to do the same thing to a given pattern. Okay, and then I also need to select how much am I going to rotate. So what's my rotate amount? Let me just make that, say, a 4-bit number for the sake of demonstration because we're doing the Brookshire stuff, right? Um, okay, then I need to say, oh, yeah, that makes sense. You saw how it complained? Well, if I have an 8-bit thing, then does it make sense to talk about rotating it by 8? It does, but it doesn't, right? Because what's rotating it by 8 actually do? Absolutely nothing, right? So what this would mean then is that on Brookshire, what's the rotation amount that you encode? It's, you get 4 bits for that. But really, do we need that 4th bit? No. Okay, so let's just make the shift amount a 3-bit thing. And if you had 4-bit data, you could always split it off to 3-bit data with the splitter. Okay, so let's connect that, right? And then U to U and U to U. And then let me make 3 different outputs here. And these are going to be 8-bit outputs. And I'll connect one of them to each of my units here, right? So I've got, we've got, which one's at the top? logical at the top, arithmetic in the middle, and rotate on the bottom, okay? All right, so let's pick a bit pattern. Let me just, for sake of demonstration, pick the bit pattern of all ones, okay? If I shift that right by 1, then what happened to the logical? Logical's at the top. Everybody got shifted, and what got put into the void? The 0. It's always a 0 for logical, okay? What about the arithmetic? A 1 got replaced there. Why did a 1 get put there? Because it was a 1 to start with, okay? And then what about the rotation? Well, the 1 on the far right came around to the far left. Okay, so that maybe wasn't the best bit pattern to have chosen. Okay, so let's change the bit pattern here. Well, let's just make this first bit a 0. Okay, so, and let's look at the arithmetic and the logical and the rotation, right? The rotation should be pretty clear by now. Just comes around, okay? What's the difference between the logical and the arithmetic here? Nothing. Why? Because our original number was positive. Okay, so the only time that the middle one and the top one are going to be different is if we have the 1 in that first position. Okay, so let's take a number. Well, first off, let's take the number 5. Okay, what is 5 in binary? It's this, correct? Okay, if I shift that by 1 unit to the right, I should get the encoding for what? 2, right? Because that's the quotient, and then the remainder is the bit that fell off in this case. Okay, good. And again, our logical and our arithmetic are the same. Great. Okay, what's the encoding for -5? What do we got to do to encode this for, huh? Do we just change the leading bit to a 1? For integers, not floats. This is we're doing integer stuff here, not floats. Well, you got to do the 2's complement stuff, right? So how did the 2's complement stuff work, Porter? What do we have to do to our bit pattern? We have to flip everything and add 1. Okay, so if I flip everything, okay, there's everything flipped, and then what? Add 1. Okay, so what's sitting in this input now is the 8-bit pattern for -5. Okay, do you guys buy that? Yeah? Okay, so what's -5 divided by 2? Should be -2, right? Because again, we discard the remainder. Okay, look at the arithmetic shift there. Okay, the guy in the middle. What does that bit pattern represent? It should be -2 if this all works correctly. Okay, but let's make sure that it is. How do I figure out what that bit pattern represents? Well, can I flip all of its bits and add 1? I can. Okay, so take the middle answer there, flip all of the bits, and add 1. What do you get? Well, if I flipped all of them, I'd get a 1 in this position, right? And a 0 everywhere else. And then I add 1. What do I get? 3. Oh, that's interesting. What were we expecting to get? 2. Okay. So what happens to the remainder when you divide by a negative by something? It actually gets included, which is a little weird, right? Okay. So does that doesn't make sense in terms of like, okay, this isn't the same as division, is it? Okay. Maybe another way to think of this is it's division, right? What's 5 divided by 2? well, negative 2.5, but if we floor that number, if we always round down, then negative 2.5 becomes what? Negative 3, not negative 2, right? Okay, now is that what we wanted in an answer? No. Okay, so if I wanted to do this quote properly, I'd have to build something more complicated. Yeah? Can you hop on Twitch, by the way, and see if Jack or Shane have any questions? If Shane is on Twitch again, I'm going to murder him for being a lazy. Yes, no, I'm not going to announce a capital crime on. Yeah.
This is like a division that has four functions.
Yeah, maybe that's best to think of it that way, as a division with the floor built into it. But it's of course not really division, right? It's just that the answers happen to be similar to what you would get if you did division. Right? Now, I'm assuming, by the way, if, and this would be something to test, right? If we went in and programmed in ARM, okay, say take the number -5 and put it in a register, and then use the integer division to divide by, say, 2, what would we hope to get? Would we expect to get -2 or -3? Yeah, or divided by 2, sorry. Yeah, I'm not sure, right? So the division unit may give answers different than the shifting unit. We don't have a division unit in the Brookshire architecture, right? It's all integer stuff only. Okay. Yeah? Huh? Yeah, we could. Well, let's find out, right? Oh. Huh? Oh, there's a bot. What's the bot doing? Yeah, of course, I can't see the messages after once the stream starts. Yeah. Okay. All right. Well, let's go in. So let me. I'm not going to fire up the Pi. We'll just do this in the virtual machine. And let me switch the input over in OBS here in a moment, guys, so everybody can see it. Huh? Come on, let's go, computer. Sometimes it's a little slow to resume. All right, while it's doing that, I'm going to switch the input to. No, just double click it. It's just Java. The first time you do it, it may take a little bit. Oh, well then, Jack was having trouble with it too, so. Hmm? Okay. Make sure this is coming through. Yes. Okay. So we're good on Twitch. Okay. So let's just make a new project here, and let's just call this shift test. Okay. And then let's just save this as main.asm. Okay. So what do we need? Data, text, global main. Okay, so what all do we want? Well, in my data section, I probably want to have a string, a format string, so I can print some stuff. So let's do Okay, and we'll do this with X registers. Okay, so let's take the number -5, right? And let's put that into there, right? Okay, now we do have to be careful. Can I actually load -5 with a single command? No, why not? Hmm? No, it does not hate it. Well, what's the encoding for -5 in 64 bits? It's a crap ton of ones, right? Well, when the move instruction, the immediate field is not 64 bits wide, it's way less than that. Okay, so what do I really need to do? Is do it in a Texas two-step, right? Load 5, but then subtract it. Do I have this right? No, I need it the other way. Subtract it from the 0 register to get -5. Okay. All right. So now I've got -5 sitting in register 1. All right. So what do we want to do to it? We want to divide it, right? All right. So what's the integer division op? It's not fdiv, that's floating. Huh? What was it? Udiv? Is it udiv? What's the u? Unsigned? Ah, well, we got a problem there. sdiv. Okay, yes, I think it's sdiv, right? All right, so let's do, well, I also need to load the number 2, right? So let's sdiv here. Let's put the answer in x1, and let's do the result of doing x1 divided by x2. Okay, then I'm going to, what am I going to put in register 0? The address of my format string. The number's in x1, so we're good, and so I can branch and link to printf. Okay, and then of course, what have I forgotten? My stuff at the beginning, although it won't actually really matter here. Okay, good. All right, so let's go into a terminal and what did I call this thing? Shift test. All right, so let's assemble it. Oh, what's wrong there? Oh, it's STP. Yeah, thanks. And this should be LDP. Yeah, duh. Oops. Okay. Okay, so we got -2, right? Now, does that make sense that we got -2? Well, huh? Yeah, the division circuit's different from the shifting circuit, which, okay, fine, right? But let's do the same thing then with the arithmetic, or sorry, yeah, the arithmetic shift and see what it gives us, okay? So in this case, what did we do? We did an arithmetic shift right, correct? Okay, so what is the opcode for arithmetic shift right? Okay, the first thing I'm going to need to do is copy and paste this, right, so that we can do the arithmetic version. And then I'll do the same thing with this part. Okay, so what do I need to change this to do an arithmetic shift. Well, what's the logical shift opcode? It was LSR or LSL, right? And you guys used LSR, right, for the fun with floats, right, with the Carmack magic number thing, right? Okay, so we just need to remind ourselves, okay, what's the thing? All right, so let's look in the manual. All right, so we want arithmetic shift. Okay, and so let's see what we got in the manual here. Address calculation, data processing, immediate, arithmetical, logical. Okay, so here's all the stuff. All right, so logical, testing, moving. Did I miss shifting? Where's shifting? Shifting on, here we go. Okay, so we've got here the immediate shift rotation, right? So we've got arithmetic shift right, ASR, that's the one we want to use in this case, okay? And then we've got logical shifts left and right and rotate right, okay? Why is there no rotate left? Well, do we need it? No, because you could always rotate right by the inverse amount, right? Either 32 or 64, subtract the rotation number. Why is there no arithmetical shift left? Because that's the same as a logical shift left. Okay, so there's no need for it. Okay, so what's the syntax for ASR is what we need, right? Okay, so what do? What's the syntax? ASR, destination register, source register, shift amount. Okay, so what's our going to be? What's our destination register? X1. What's our source register? Also X1. What's our shift amount in this case? Just the number 2, which happens to be an X1, right? So I could do this, or I could do that, right? Is that okay? What's wrong? Oh, by 2, sorry. Yeah. Okay, if I'm shifting, if I want to divide by 2, then we're shifting to the right by 1 position, right? So it helps for your professor to not be a moron. Yes? Okay, so let's run that and see what we get. So I therefore don't need this instruction. Okay, so let's group those here. All right, and I can reuse the same string, but let's actually make a new one, right? So this one, let's say the division answer is blah. The arithmetic shift answer is blah. And then we'll put this one num string 2. Okay. All right, so let's reassemble it and see what we get. Symbol, link, execute. Aha. It's exactly what we thought. Or exactly what we deduced, because we're smart like peoples. Okay, so what's the moral of the story? Huh? Well, yeah, I guess use estiv, but I don't know, maybe there is a reason that we would want to have done it this way. And I can't think of anything off the top of my head, but right now the floor operator, you guys have seen that plenty in like, let's say, have you guys talked about floor in Math 108? Those of you who took it or are in it? Yes? Okay, Michael's nodding his head vigorously over there. Okay, and then what's the, to go with the floor function, we've of course got the ceiling function, right? So what's the difference between flooring, ceiling, and rounding? Right, rounds down. Ceiling always rounds up, floor always rounds down. And rounding, yeah, to the nearest, or to the either nearest above integer or nearest below integer. Okay, what does rounding do? Well, there's that whole 2.5, like, so if I have 2.5 and I round it, what do I get? 3. If I ceiling it, what do I get? If I floor it, what do I get? 2. Okay, but if I have 2.4, if I round it, what do I get? If I floor it, I get, and if I ceiling it, I get, right. Okay, so yes. Okay, good. Yeah. Has the floor or ceiling come up in what other class, like data structures or 111? What about those of you who are in numerical analysis? Have you guys had to use that at all? No? Okay. Um, yeah. Okay. Anyway, that was enlightening, right? So we've deduced, right, that, well, and this shouldn't come as a shock, that the shifting unit and the division unit are not the same thing. Okay, why shouldn't it come as a shock? Well, I've got multiple opcodes, right? Why would I have several opcodes that in effect do the same thing? That's silly, right? It's inefficient. No? Well, okay, that's the, yes, yes, yes. Okay, good point, right? Does this bit shifting stuff help me divide by 3? Nope. Huh? If I had a Russian computer. Well, he's, he's not wrong. So it turns out that, and I don't quite understand why. I haven't read this stuff and deduced through it, that the optimum number of bits to have to base your computer on is E, 2.718, blah, 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 blah. Okay, and that's like some sort of like information theory, something or other. Okay, well, what two integers are very close to 2.7? 2 and 3. 3 is a little closer, right? So in an optimization sense, a tri-state computer would actually be better, I think. And so the Russians actually built one of these things. It did digital logic, but it did it with 3-state instead of 2-state. I have no idea how it worked. Huh? I think, but surely there's something more to it than that, right? Um, yeah. So anyway, um, yeah. So Dr. Brown, I forget, he and I were talking about this sort of thing one day, and he's like, "Oh yeah, and the Russians actually built one of these things." So yeah, we really should do a CS341, Advanced Machine Organization. Would you guys take it, or would you like run for the hills? Medium sized, like what you want? Medium with a side of ranch. Okay. Fun size? Yeah, I guess, right. Well, I mean, this is like, I think we're doing like B-dubs medium, right? The B-dubs hot would be like what you're describing. And what I'm talking about is let's do B-dubs Carolina Reaper. No? Well, you'll be gone. Okay. Yeah. So, yeah, anyway. Well, okay, so let me actually get y'all's opinion on things. So, um, I don't know if this will work out or not, but I would maybe sometime next year like to offer. Um, so, okay, CS majors, right? You guys have to take some electives. Yes. Okay. Now, some of you guys are taking the operating systems class next semester. Who is taking that, by the way? Yeah. Okay. Huh? The operating systems class with Dr. McCartan Lim next semester. Yeah. Okay. So that will count as one of your electives within the major. Okay. Um, Well, so every semester-ish, we want to have at least one of these things, right, to pick from. Um, Stuff like numerical analysis. Did you take that as math or as CS? Okay, so it'll count as an elective there too. If it's cross-listed, you could do it either way. Um, but what I'm just kind of kicking around in my head is at some point, maybe next year, doing here. So here are the ideas I have. One would be full semester advanced machine organization. Okay, to basically keep going with what we're doing and actually do more circuit level stuff and maybe build some things. The others would be sort of variations on that. One would be um, retro computing and spend like half the semester talking about the Apollo guidance computer and half the semester, say, talking about the 8-bit Nintendo. Yeah, you think? Yeah. Well, what about a full semester course on the 8-bit Nintendo? Like 8-bit. That sounds the most fun. Oh yeah. Be careful what you wish for, though, huh? Well, I was trying to learn some of this stuff last year. I'm still working on it, but yeah, the like yeah. Well, I've got some boards that have the same processor that was in the Super Nintendo, but and I was trying to kind of figure out the assembly there. Okay, so yeah, so which of those like what seems the most interesting to you guys? The last two? Okay, that's kind of what I figured, but yeah, I'll see what I can come up with. Um, huh? Whole semester in Nintendo? Yeah, a choice. Actually, that's as amusing as that suggestion is, it's not actually too far off from what I was thinking about, which is not to Japan, but um, so there are, well, okay, let's just pretend that COVID never happened, right? Okay, and that because in the before COVID times, right, BC era, right? Okay, no, I'm stealing that one from the hotels.com commercial with Captain Obvious. Yeah. They have one where it's like BC 2019 and they have, the actor that does Captain Obvious. There's sort of two versions of himself and he's like from the future telling the past guy like what's about to happen and stuff. Okay, anyway. Um so before COVID, right, when people were still traveling a lot and there were conferences and conventions and things like that, well, there are game conventions, right? Now, you guys know about the big ones, obviously, like E3, and, well, which is way more than just gaming, huh? Yeah, TwitchCon, BlizzCon, QuakeCon. Heck, I used to work QuakeCon back in the day. Okay, but there's lots of these things, and some of them have like the Game Developers Conference or like Indie Game Fests or things like that, where people are coming and presenting like their projects. That would be the idea, yeah. Yeah. Well, okay, maybe as teams, but yeah, I don't think you're going to make millions of dollars writing a program for an 8-bit Nintendo. Well, that's true. If it's really good, who knows? Now, here's the crazy thing about 8-bit Nintendo development. You can actually buy cartridges like they're the size of the classic Nintendo cartridge and write your data to them and pop it into a real Nintendo and power it up and it'll run. I know, like right. Um, yeah, what do you think's on my Christmas list this year? No. Well, actually, yeah, I do want to start building a collection of retro gaming and computing hardware. and like have a little lab upstairs with like a Nintendo and a Super Nintendo and a Sega Genesis and a N64. The N64 was really interesting from an architectural standpoint. Um, huh?
If you're playing a game, if you want to like change one like thing about it.
You could actually. So this is kind of old school, right? But did any of you guys have either an 8-bit Nintendo, a 16-bit Nintendo, the original Game Boy, or I think a Sega Genesis and maybe an N64? Okay. No, like the original Genesis, which was like with the original Sonic the Hedgehog. No? Okay. How many of you guys had a Game Genie or have ever heard of that thing? Okay, so what's a Game Genie do? Well, yeah, so a Game Genie you put in between the cartridge and the console, okay? And what it does is if you go in and you put in like codes, but what that does is it tells the Game Genie how to mess with the data that's in memory. Okay, so let's say, for example, that the number of lives that you have is stored in a particular memory cell. Well, you could go in and change that memory cell to be like 255, and then you have 255 lives in Mario instead of 3 or whatever it starts at, right? Now, that's kind of a sedate thing, but you could do a lot more crazy stuff with it, like, invulnerability. And basically, what it would do is like, if you got shot, it would disable like certain parts of the code or whatever. It's kind of voodoo how it works, but yeah. Or actually, this stuff is in movies. How many of you guys have seen The Martian? Yeah. Okay. So what happens in The Martian when um, they realize that he's alive? Okay, and he drives and gets that old like rover from a previous Mars mission, right? And he sets up like the little flags A through Z and 0 through 9, kind of in a circle. And then based on which way the thing's pointing, they can send him messages. Well, one of the messages they send is change memory address blah from blah to blah. And then so he goes in and hex edits certain part of the operating system code, and then that allows them to use the direct communication stuff, and then he can type messages instead of having to do the like little camera rotating around thing, right? It's kind of like that. Yeah. So okay. All right, well, we'll quit a little bit early, but let's talk. What are we going to do on Tuesday? Okay, so there are two things that I'd like to talk about on Tuesday. The first is structs, okay, which is kind of like objects in a sense, right? So a struct would be something like, um, I want to have a customer, an object that has multiple data types underneath of it. So, for example, I could have customer that has a string for their first name, a string for their second name, a number for their age, a number for their phone number, or something like that, right? So a compound data type that's built out of several more primitive data types. Okay, so what we want to do is look at those, how they work a little bit in C, how the pointer stuff works with them, and then look sort of how that stuff looks when we're in assembly. Okay, so if we compile it, then what? Then what? Okay, that will be helpful at least as an amuse-bouche for those of you who are taking the operating systems class next semester. That was a request from Dr. McCartan Lim. The other thing that we need to talk about are what are called atomic instructions, and not in like the Fallout 4 kind of sense of Nuka-Cola, okay, but an atomic instruction basically, um, when we're running this stuff on the Pi, okay, we're running a single threaded program and it's going to be run on a single core on the Pi. But the Pi actually has 4 cores, right? And so there could be other programs running. Well, what happens if multiple programs are trying to use the same memory addresses? what theoretically could happen? Well, bad stuff, yes, but let's be a little bit more descriptive here. What do we mean by bad stuff? Well, let's say that one thread writes to a memory cell, and then another thread reads from that memory cell and gets a value that it wasn't supposed to get, and things are out of sync, right? Things can get really messed up. Okay, so what we want to kind of talk about is how instruction set level stuff can allow you to like lock, if you will, memory addresses. This would be particularly useful, well, like say for the GPIO stuff. Let's say that I had two programs that were both trying to access the GPIO memory at the same time. Well, if they're both reading from it, then it's not really going to be a problem. But if one of them's writing to it, well, we might have issues. Okay. So we'll talk a little bit about that also, and just kind of as a preview of coming attractions for those of you who take something else. Okay. The last thing is, when is the drop dead absolute latest time that you can submit or resubmit anything? The 24th at noon, which is when our final exam would have ended if we had a final. Okay, so please keep trucking. Some of you owe me lots of stuff. Some of you owe me a little bit of stuff. Oh, also one other just quick announcement. Jamba believes that there may be a typo in the book SIMD sign routine. I haven't gone through it yet to make sure, but just FYI. The other thing, and I didn't realize this, is what does the book sign routine for 64 bits go up to? It goes up to x to the 21st, okay, not x to the 15th, right? Which means you can like lop off a couple of instructions at the end, or just replace some of those coefficients with zeros. That's the lazy way, okay? Okay, good? All right, see you guys Tuesday, if not sooner. Have a great day. And those of you guys who are online, you take a class on Nintendo. Who's NAHS? Who is that? It's not Jack. I don't see Jack on. Yeah. Well, anyway. All right, I'll see you guys later. Have a good day.